I actually can't juggle. But brings up a really good point. What is gravity? I mean, I know we've already talked about gravity as a force, and it's a force from the Earth pulling on you. And we know that to find an object's weight, or the force of gravity from the Earth, you take an object's mass and multiply it by the acceleration due to gravity, g. But what if you're not on the Earth? What if you're talking about two different objects outside of a different planet? What if you're talking about a whole new planet in general? What if you're looking about the force between two stars or two planets or two things not around the Earth? How do we find the force of gravity there? Well, that's what this video is about. Here we are going to look at Newton's law of gravitation. Here we are talking about gravity, or the gravitational force, and we've already talked about gravity, or F of G. Now remember, it wasn't just gravity. This is actually more accurately an object's weight. And remember that we find this object's weight by doing mass times the acceleration due to gravity. Now, what this is talking about is finding a single object's weight or gravitational force between it and something way bigger, like the Earth. And this is dependent on knowing g, which is the acceleration due to gravity. But the question becomes, well, what if we didn't want to know just about a single object or small object on a bigger object? What if we wanted to find like two comets flying around, or the gravitational force between the Earth and the Sun? This is going to talk about big G. So we need to make sure that we don't screw up the differences between F little g and F big G. Now remember, F little g is weight, and we're just pretty much talking about a single object on like the Earth. Big G is talking about the gravitational force between any two objects. And what we are assuming about these objects is that these objects are circles or dots. So if we're going to look at the gravitational force between two large objects, we need to know, well, what is it related to? What is it dependent on? Newton realized that, well, it's dependent on not only one object, but two objects. And the bigger each object is, the greater the gravitational force they will feel between each other. So if I double the size of M1, let's say that's 2 times M1, and I leave M2 the same, the gravitational force is actually going to be 2 times the original gravitational force. So if I increase the mass of one, the other one gets bigger. And same thing as if I increase M2, this force will get bigger. So Newton, what he realized is that the gravitational force is directly proportional to the two objects' masses. Now, Newton also realized that not only does the gravitational force is dependent off of the mass of the two objects, but it also depends on their distance between each other. So if I take M1 and I increase the distance away from M2, he realized that the force goes down. And what we say is that the distance between these objects are r. So what he realized is that the gravitational force is inversely proportional to the distance, which we're going to call r. So that r is the distance between the two objects. So what's really interesting is that Newton realized that this is actually the incorrect relationship. It's not related to the inverse of the distance. What he saw is if you took the distance between two objects, you're going to have some sort of gravitational force here. But if you doubled the distance, he actually noticed that you're going to have 1/4 of the original gravitational force. And so let's say you tripled it. Let's say, okay, you move the distance between the two objects 3 times the original distance, 3 times r1. You actually notice that the force of gravity, the gravitational force between the two objects, went down 1/9. This gives the idea that it's related to the inverse square. And this is actually called the inverse square law, which means if you double the amount of distance between the objects, the force of gravity will actually get 4 times smaller. And if you triple it, it'll actually get 9 times smaller. The big idea here is the squared term that I just covered up the 2. So the whole idea is it's the inverse square, not just the inverse, but inverse squared law. So the more and more that the objects get away from each other, the force drastically drops. So we're almost there. So we have that the gravitational force is directly proportional to the 2 masses of the 2 objects, and inversely squared proportional to the distance between the 2 objects. Now, if you check out your equation sheet, we come to find that the gravitational force between 2 objects is equal to g times m1 times m2 over r squared. Now, you might be wondering, what the heck is this giant G? So what this big G is the gravitational constant. So that just means in our universe, there exists this constant of 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. What does this all mean? Really, this is just kind of a filler. So we know that we can find the gravitational force between 2 objects. We know it's directly proportional to the 2 masses and inversely squared proportional to the distance between them. But there was some stuff missing, and this is all the missing stuff. Yeah, that's pretty much it. But a couple things to point out is how weak this gravitational constant is. We want to look at this negative 11th power. That makes this number really, really, really small, which really tells us that the gravitational force, or the force of gravity, is pretty weak. So that pretty much sums it up, that the gravitational force talks about 2 objects, and it's related to g times m1 times m2 over r squared, where g is the gravitational constant. The 2 masses are m1 and m2, so depending on how big your masses are. And r is the distance between the 2 objects. And just to remind you, it's the center of the 2 objects. It's not this distance. It's actually the distance from the center of this object and the center of that object. That is our r. All right, so we just got done explaining Newton's law of gravity. So we now have a relationship between 2 objects and the amount of force between them. But that's not actually 100% accurate. You see, Newton's law of gravitation is a great approximation. It's a great way to get us to the moon, but for actually being 100% correct, there are some problems with it. The one thing that Newton didn't really do is he didn't explain, well, what was it? Why do objects of 2 masses attract each other? This actually was answered by Einstein. Einstein came up with the idea that it's not just space, but it's space-time. And you can think of this space-time as a fabric, like we've got here. And on this fabric, we have different objects. Now, we can think of ourselves as these little ping pong balls. As you notice, they're not really attracting each other right now. That's because they're super light. They don't really do anything to the fabric of space-time. Even if I take something a little heavier, it makes it ripple a little, but nothing big really happens until you get such a massive object that it begins to warp and pull things inside. So for instance, if I back this up a little, if I place the sun, down it comes.
it attracts other masses around. What it does is it warps space and time, which brings objects in and around together. In fact, if I can get this to go smooth, that helps show why some objects, like asteroids or moons or whatnot, get pulled in. It's because it bends the fabric of space and time. Pretty cool!